Hello, if you have been following along, this is the last video in a three-part series about chaos animation. In this series, we are exploring the math and programming behind animating chaotic systems. This video will discuss the nonlinear, dynamical, double pendulum system. We are all familiar with the single pendulum, found in objects like grandfather clocks. It oscillates back and forth in a predictable manner. Higher starting velocity leads to higher displacements, and so on. But what happens when a second pendulum is attached to the mass of the first pendulum? As it turns out, interesting dynamics unfold as we seek to animate in this video. We first need to understand how to keep track of this complex system's positions. There are two mass bobs, M1 and M2, which are highlighted in beige. They are separated from each other by strings of lengths L1 and L2. These strings are at angles, θ1 and θ2, from an imaginary central vertical axis. We need to add the double pendulum's equation of motion into the simulation now. The following complicated equations model the second derivative of change in angle with respect to time. This is also known as angular acceleration. Now, we need to get this angular acceleration value to a discrete angle so that we can translate it into x and y positions. This is done through the following method. The angular acceleration is equal to the equations of motion for the double pendulum as we described. The angular velocity is equal to the previous angular velocity plus the angular acceleration times a times elapsed constant dt. The discrete angle is then defined as the previous angle plus the angular velocity times this dt. This is a simplified numerical method for solving differential equations like the double pendulum's complex equations of motion, known as the forward Eulers method. With the discrete angle, we can then perform the following trigonometric equations to determine the x and y positions of the two mass bobs. These points are then used to render the calculated points as filled circles with straight lines connecting them. We can then set some initial parameters, such as the angle of extension of the two bobs, angular velocity, mass, length, gravity, and time elapse, dt. The program will continually change these calculated points based on the double pendulum's equations of motions in real time using the drawing parameters we just described. To model the chaotic effect of the double pendulum, we repeat this 2 more times for the total of 3 double pendulums. After all of this admittedly hard work, we can finally enjoy our satisfying real-time animation. Below, I only deferred the mass of the bobs by 1 unit each across all 3 of the double pendulums, and the chaotic effect still unfolds. Thank you for making it to the end of the video. The animations used in this video were generated in Python. I have linked the program in the description for those of you who are interested. That being said, please like and share this video, subscribe if you enjoy and would like to see more of this type of content in the future. Goodbye!